A very good afternoon, honorable guests, speakers, ladies and gentlemen, and good day to our friends from all over the world joining us live through our live webinar platform. A big welcome to Masterminds Masterclasses, organized by the Council of the Hong Kong Laureate Forum Limited, also known as the HKLF. My name is Marcus Kwok. What an absolute honor to be part of this wonderful event. So the HKLF aims to promote understanding and interests of young generation in science and technology, as well as to foster the exchanges among scientists of different generations, cultures, and disciplines. By organizing the Hong Kong Laureate Forum, the HKLF will invite recipients of our homegrown Shaw Prize and global renowned scientists to have direct academic exchange events with selected young scientists from around the world. Before the launching of the inaugural Hong Kong Laureate Forum in November 2022, we have embarked on a series of pre-forum events to cater for a variety of audiences and to further the HKLF's mission of providing a platform for scientists with different expertise worldwide to come together, to promote science, and to enlighten the younger generation in the scientific community. The first chapter of the pre-forum events, namely Science Exposition, was held successfully in September and October. Today, we will continue the second chapter of the Prelude with the inaugural Forum Masterminds Masterclasses, which offers an invaluable platform and opportunity for young scientists to have an inspirational and intellectual exchange with prominent scientists. Yesterday's forum was about life science and medicine. Today is about astronomy, and tomorrow will be mathematical sciences. What makes today's seminar super special is that two of our speakers will be joining us live through a 3D holographic projection. You see very soon. I can't wait to see it myself. All right, to kick off today's seminar, we're very honored to have Professor Kenneth Young, board member of the HKLF, joining us in person. Professor Young is also going to be our moderator for the panel discussion. Professor Young is a theoretical physicist and emeritus professor of physics at the Chinese University of Hong Kong. He's also the council chairman of the Shaw Prize and vice chairman of his board of adjudicators. So ladies and gentlemen, please welcome Professor Kenneth Young to the stage for a welcome remark.
Thank you for the kind introduction. Young people, ladies and gentlemen, welcome to this forum organized by the Hong Kong Laureates Forum. And the seminar for astronomy is the second event in the series that we have coined Masterminds Masterclasses. The concept behind Masterminds Masterclasses is for renowned scientists to share their work, their research journeys, and their personal takes on the road less traveled. Their sharing will help aspiring young scientists, I see many here, to map out their own research journeys and plan their science pursuits ahead. Get ready for an inspirational and aspirational, thought-provoking session. The masterminds for this session on astronomy are three astrophysicists who have spent many years studying the mysteries of our universe. They are interested in many and diverse things, but in a way, their work all have something to do with dark matter from different perspectives. Joining us from Paris is Professor Françoise Combet. Even though she cannot be with us in person, she is being beamed in and will be sitting on stage in three-dimensional form. Professor Françoise Combet is the chair of Galaxies and Cosmology and professor at the Collège de France and an astrophysicist at the Observatory of Paris, PSL. She has won numerous awards for her work on galaxy formation and evolution, which paved the way to better understand the role of supermassive black holes in the centers of galaxies, supermassive black holes. Recent awards include the Gold Medal of CNRS 2020 and the 2021 L'Oréal UNESCO International Award. Professor Combet will speak on black holes and galaxies. The second guest, Professor Simon White, is a Shaw Laureate in astronomy from a few years back, 2017, and he will be joining us from Berlin. Professor White is also joining us through holographic image. Professor White is the Emeritus Director at the Max Planck Institute for Astrophysics. Max Planck Society, under which the Institute operates, is a world-renowned science and technology organization, research organization. Over the years, 37 of its scientists have received Nobel Prizes. Professor White's main research focus is on the formation of structure in the universe. If there were no structure, we wouldn't be here. And joining us physically is our third guest, my colleague, Professor Chu Mingzhong, MC Chu, from the Department of Physics, Chinese University of Hong Kong. Professor Chu has spent decades studying the interactions of neutrinos and their role in the universe. The collaboration of which he is a part, working at Daya Bay on the transmutation of one form of neutrinos to another, has been awarded the Breakthrough Prize. Understanding neutrinos could be one of the keys to unravel the nature of dark matter, which in turn may help us to understand the evolution of the universe. Professor Chu will share with us today on the neutrino universe. So do enjoy, and I hope you will end today with many lessons learned. Okay?
Thank you. Thank you. Now, we're extremely delighted to have three renowned scientists in astronomy joining us today and sharing their research experiences. After each of the presentation and panel discussion, our scientists will answer questions from you too. Now, for our online friends, you can ask questions too during Q&A. All you have to do is simply click the Q&A window and submit your questions via the Q&A box. Selected questions will be answered by our scientists. All right, so without further ado, our first presentation of the day. May we invite Professor François Combe to join us live from Paris. Professor Combe is an astrophysicist at the Paris Observatory, Chair of Galaxies and Cosmology, and Professor of the Collège de France. So ladies and gentlemen, please welcome Professor Combe. All right.
So thank you very much. I'm very pleased to be here. And I will talk about black hole and galaxies. We have been very pleased to have a lot of knowledge in the recent years about black holes. So although these in the 18th century were intuitively guessed by Mitchell and Laplace, that they have guessed that there are some compact objects that are so compact that the escape velocity is larger than the velocity of light. In fact, it has to wait Einstein and its general relativity to really have a nice view of the black holes. You see that gravity is not a force like others. It is like a deformation of space. And already in 1916, Schwarzschild has solved the Einstein equation to show that around a body in a spherical symmetry, there is a radius that we call horizon. And if you are inside the horizon, there's nothing can escape, not even the light. So it's an event horizon. And of course, at this epoch, even Einstein did not believe that these objects were really existing. There were chimeric objects from the equations. And of course, people thought that when a star explodes in a supernovae, they will be dispersed all the way around. But in 1963, Kerr solved the equation for a rotating black hole, but again with symmetry, so it was not yet convincing. It's only Penrose in 1965 that solved the problem by topological trick, in fact, looking at trapped surfaces. And he convinced people that the existence of black hole was ineluctable. That's why he got the Nobel Prize in 2020. Now we know that the black hole is like a singularity in the deformation of space, and it is described by mass and spin. So we were very pleased to have in 2019 this breakthrough that you have a first image of a black hole shadow. In fact, you see here in the top left that you have a circle of orange circle This circle is emission from a plasma, ionized gas that is swirling around a black hole. And you have a black hole, exactly, which is a shadow. In fact, it is not the horizon. It is 2.5 times the horizon. But it is a shadow because all the photons there are trapped by the black hole and cannot get out. So the presence of this shadow is a proof that there is a black hole here. And this image has been obtained. It is a challenge, in fact. It has been obtained by a very large baseline interferometry, VLBI. VLBI was known for decades in the centimeter wavelength. And you see here at the bottom right that this galaxy, M87, which is the biggest galaxy in the Virgo cluster, has already been shown to have a jet. The black hole is ejecting some gas. You have a jet at 4,000 light years scale. You can make a VLBI, very large baseline interferometry, having a telescope all over the world. So you can have a base which is 12,000 kilometers. And then you have 0.1 light year resolution. But if you increase the frequency, you go to millimeter wavelengths, then it is more a challenge because the atmosphere of the Earth is limiting you. It's very turbulent, there is water, but this is a challenge that people have of the Event Horizon Telescope have raised here. So they have been able to have 40 micro-arcsecond resolution to see this gas swirling around the black hole. Of course, the image is a first breakthrough. It is still a little fuzzy, as you see in the top left. And what we would like to have, it's even more resolution to see in the middle, like a simulation of the photon ring. There is a last circle of photons that can circle around the black hole. And the size of this photon ring will give you the spin of the black hole. So this is quite interesting. And to have also in orange, the last stable orbit of the matter, the plasma, which is soaring there, will give you also whether the plasma is rotating in the direct or retrograde sense. But this is for the future. There are many things to do yet. Well, there is two kinds of black holes. There are stellar mass black holes, and these are formed when a big, massive star is exploding in a supernovae. Then the envelope is getting out, and the residue, if the residue is larger than 3 solar mass, there's nothing stopping the gravity, and you have a black hole. And these we know then for a long time because some are in a binary star. So you have a normal star swirling around the black hole. The normal star is giving some mass by the Roche lobe to the black hole. There is an accretion disk. And of course, you see all these gas which is shocked and emitting in UV, in X-ray. So you see these X-ray binaries. And of course, you see also the velocity, the orbit of the normal star. And you can guess what is the mass of the unseen star, and it is a black hole. You have several black holes like in the galaxy. But what we are interested today also is the supermassive black hole. There is one supermassive black hole in each galaxy, in each nucleus of galaxy. And it is from millions to billions solar mass black holes. It is really another scale of mass, and in between you have the intermediate mass black hole that nobody has seen yet. And what very interesting things to notice is that since the radius of the horizon is proportional to the mass, the average density of the black hole is inversely proportional to the square of the mass. So this means that the big black holes, which are larger than 100 million solar mass, they swallow their stars without sharing them by tidal interaction, and you don't see any manifestation. So here you can see in the top some visualization from Luminé. And if you have, for instance, an accretion disk which is edge-on, you don't see really a thin disk, but you see some kind of image like a Mexican hat that you see here. Why? Because the light is deflected by the black hole and it can come above and below. And you have maybe seen this image from the movie Interstellar, which is very close to the reality. The best supermassive black hole that we know the best is the one in our own galaxy, the Milky Way. You see here face-on view of the Milky Way. It's an artist view because we are inside the Milky Way and we see only an edge-on view like you see in the right. So the sun is in the yellow position in the middle of the disk, and the size of the Milky Way is 100,000 light years. So it's very big, but we are going to make a zoom to the black hole in the center. You see here that we have a zoom to 1 light year, so a zoom by a factor 100,000. You begin to see the stars around, and the stars are very fuzzy because of the turbulence of the atmosphere. Normally they should be point-like, but you can use adaptive optics to align the wave front that are very perturbed. So you align the wave front and you can retrieve the point-like nature of the stars that you see at the image at the right. And of course, they are not completely point-like. They have the shape of the diffraction pattern of the Very Large Telescope. This image was taken with the VLT, Very Large Telescope, at ISO in Chile. Now, when you make this vision with adaptive optics in the near-infrared wavelength, you can follow the stars, and that's what the two groups have done. An European group led by Reinhard Genzel that you see in the bottom left, and also a Californian group by Andrea Ghez, and they both share the Nobel Prize in 2020 with Penrose. Why? Because they have been able, by their 20 years monitoring of the stars in the galactic center, to show that there is a very supermassive black hole in the center, which is about 4 million solar mass black hole. So you see in the motion, the little animation here, that there are several stars rotating around the black hole. You see that there is a yellow one, which is the closest one, that the star S2, that is making like a Keplerian orbit because you are dominated by a point mass, the black hole. And this orbit has a period of 16 years. It has passed near the black hole in 2002 and also in 2018. And in 2018, the European had in the VLT at ISO a very sophisticated instrument, gravity, which is an interferometer that's able to combine the radiation from the 8.2 meter telescope of the ISO, the 4 VLT telescope. So if you combine the radiation from this 4 telescope, you can have the equivalent of a telescope of 130 meters and have a high resolution. And you can have a resolution of 40 micro-arcsecond. And then you can see, here you see the orbit and the passage to the pericenter. You have 4,000 kilometers per second in velocity. And you can check all what is predicted by general relativity, that is redshift, the gravitational redshift, and also the precession of the orbit. And even better, what they have been able to show is the flare that you see in the center, in the left image. You have an animation where all the stars are flickering still because of the turbulence of the atmosphere. And in the center, you see that the black hole has a flare. And this flare is the gas rotating around the black hole that you see coming towards you and behind. And it is rotating at a period of 40 minutes. So you have to catch very quickly, and they have been catch here by 40 microarcsecond. And why they have not been able to do an image? Because in the infrared, the atmosphere is not stable enough. And why the Event Horizon Telescope in the millimeter have done the image of a very remote galaxy M87, which is 2,000 times farther than our own galactic center, while the black hole is 2,000 times more massive, coincidentally. And they have been able to do the image of this far away black hole and not our own, because our own has a very, very short period, and the source is visible only for a quarter of an hour. It was not possible. So there is also a big event, a breakthrough, is in gravitational waves. We learn now much more about black holes because of these waves that were predicted by Einstein, and he did not believe that it was possible, but with LIGO and Virgo, it was possible to measure a very tiny difference of length by deformation of space of 10 to the minus 21. And you have seen maybe this event of waves during the merging of two black holes, which is lasting only less than a second, and two black holes of 29 and 36 merge, and finally they let three solar mass of energy, E equal mc squared, to deform the space during 1.3 billion years of the path of the light. And now it is an industry. We have detected 50 mergers of galaxies, of black holes, sorry. And we have been able to find very massive black hole, like 142 solar mass black hole. It's very interesting because we are entering this gap between the solar mass black hole and the supermassive black hole. So maybe we are understanding how the small black holes merge, and recursively towards forming intermediate mass black hole and the supermassive black holes. And I will now also finish by telling you how a supermassive black hole can impact a galaxy. In fact, we have noticed that there is a very good relation between the mass of the black hole and the mass of the bulge of a galaxy. You see in yellow the bulge and in the disk in blue. And the black hole mass is only 0.2% of the bulge of the galaxy. This means that with respect to its mass is very negligible, and the action it has on its galaxy cannot be the mass, but it is the energy. Because when a gas is falling onto this very high gravity object, then the gravitational energy is so huge that you have a lot of UV, X-ray radiation, and the radiation pressure is sufficient to get the gas out. So you are ejecting a lot of mass. Here, maybe the supermassive black hole can solve the problem that we have with dark matter. Here we know that in the universe you have only 5% of atoms, ordinary matter, 25% of dark matter, and the rest is dark energy. But in a galaxy that you have in the left here, you have atoms in the center mainly, because atoms are dissipated, and the dark matter is a halo around the atoms. But while in the universe you have a fraction of atoms to dark matter, which is 20%, in galaxy it's much less than 4%. So we don't understand why in making a galaxy we are losing a lot of ordinary matter that is ejected outside the galaxies. 80% of the atoms are outside the galaxies. Why? And we think that maybe it is the supermassive black hole that have enough energy to eject all this matter out of the galaxy. And indeed, we see some of evidence of this energy here. Here you have in red the hot gas that are in galaxy clusters, a cluster of thousands of galaxies. In the center, you have the biggest galaxy, and you see that there is a supermassive black hole inside, ejecting a jet of plasma in blue, and the plasma is sculpting some cavity in the atomic gas that is most of the gas of the galaxy cluster. So we have evidence, indeed, that there are some energetic pushing by radiative pressure of the atoms outside of galaxies. We see here also in this Perseus cluster, you see in the top left some yellow image of X-ray emission of the very hot gas, hot atoms, plasma, and you see that cavities have been sculpted there from the supermassive black hole in the center that push the gas. And you see also in the bottom right some black contours that are around the jet of the supermassive black hole. This is molecular gas. So this means that the supermassive black hole is able also to push molecular gas. Molecular gas is very important because it is in this molecular gas that you form stars. So if you push the fuel to form stars, you are also stopping the star formation in galaxies. So the supermassive black hole are able to stop the star formation in galaxies. And here you see that when you are very close to the black hole, you have the jet, the wind, and we have detected very close ultra-fast outflow due to the supermassive black hole. This is seen in the line, the Doppler shift of the line. The line is ionized gas. It's iron 25 or 26. It's very ionized iron because it is 10 million degrees. And the gas, by Doppler velocity, you see it's 10,000 or 20,000 kilometers per second. It's very fast flow, and this flow is not a lot of mass, but it is pushing the molecular gas that you see here cartoon. The orange flows here are all the molecular gas that is ejected outside of the galaxy. And you see in the spectrum that the gas is ejected at 1,000 kilometers per second. And it is not a lot of velocity, but there's a lot of mass. So a lot of the interstellar matter of the galaxy is pushed away. And indeed, you have all the gas getting out of the galaxy. This is seen for high activity of the supermassive black hole, but it is true in every galaxy. This is an example of nearby galaxy, which is a very low state of nuclear activity, a Seyfert, and still you see an outflow of 63 solar mass per year, which is 10 times the rate of star formation. So indeed, it is possible to show that the supermassive black hole are living in symbiosis of their galaxies. They are growing together with the galaxy, but they are also regulating the star formation, and they are regulating the growth of their galaxy host. There are ultra-fast outflows that are observed around very massive supermassive black holes. And finally, the feedback due to this radiation pressure, the winds and the jets, are able to explain why all the atoms are getting out of the galaxy. 80% of the black holes are getting out. Thank you very much.
Thank you. Thank you, Professor. Oh my God, that was phenomenal, isn't it? It's mind-blowing, isn't it, when you think about the black hole and you think about the universe, like everything seems so tiny, including ourselves. It's very humbling. So, Professor, how are you today?
Oh, nice, very nice.
Now, before we move on to the Q&A, I just want to clarify one thing. How do I pronounce your surname correctly? Did I say it okay?
It is Combe. You don't see Combe, but Combe. Well,
Combe.
It's in French, it's difficult. You have a mute E.
All right, I learned something today. It's Combe. All right, Professor Combe, the first question we're going to take from online. And the question is, what motivates you to do research in astronomy? And why are there so few women astrophysicists, in your opinion?
Well, it's good questions. First one, well, in fact, I was not completely motivated to do astronomy when I was young. I was motivated to do research. I was fascinated by all the great researchers, Marie Curie or Pasteur, even in biology. So I didn't know in which domain I would do research, but I was really fascinated by the research, discovering things. And at the end of my studies, I was inspired by professors at the École Normale who was doing some astrophysics and cosmology. So my first work in astronomy was cosmology, and I was working on the Big Bang, how you can have a symmetric universe of matter and antimatter. But then it did not work, so I went to observe molecules in interstellar matter and galaxies. And why there is few women, in fact, I think it's all the same problem in physics, in all physics. In fact, there is some stereotypes in the young age. Girls are convinced that they are not good at science, very strong science, and they are better to do literature or human science or social science. So there are many women that are convinced of that because of the culture. So we have to change that because they are very good also at science and we need their competences. And I hope it is changing progressively. And there are more and more women now in astrophysics and physics in general. They're 30%, so it's better than before. And I hope that in the future there will be even more.
Well, you have definitely proven them wrong, and you are someone we really, really look up to. Okay, we're going to take the next question from the floor here in Hong Kong. Anyone with a question? Just raise your hand. Yes, we have a question already. In the middle row. Right. Go ahead.
Recently, there was a discovery of a black hole that was spotted lurking in a young cluster of stars that is only about 100 million years old. So my first question is that simply what does it mean for there to be a black hole to be around such a young star cluster? And my second question is that how can the black hole simply enter the cluster? Yeah, so that's it.
All right, wow, a very interesting question.
Yes, it's a very recent discovery in NGC 1850 in the Large Magellanic Cloud. In fact, the there is no surprise to find a black hole in a stellar cluster, globular cluster, as I've shown that in a cluster you have 100,000 stars in a very small volume, 3 light years. So they are colliding frequently, and you expect to find many black holes in stellar clusters. But this one, it is not sure that it is a black hole, in fact. It is difficult because there is a binary and there is an orbit, but there are some uncertainties, and I have no time to discuss the uncertainties, but there has been, even this morning, a paper on the archive saying that maybe it's not a black hole, it could be a neutron star, because they are wrong in the mass of the normal star that are orbiting the black hole, and it can be overestimated. So if it is overestimated, you overestimate also the mass of the companions, the mass of the unseen object. Could be a neutron star, so maybe it's not a black hole. But in fact, this method is very interesting. It's a method of a binary. So you observe the normal star around, and you deduce the mass of the binary to know if it is a black hole.
So there you go. A very good answer, isn't it? All right. Now, we still got a bit of time, so we will take one more question from online. So the question is, Professor, what will be the future astronomical construction look like?
The future, it's a big, big question. As for the topics of today, the black hole, in fact, we hope to have much better resolution. And I've shown in the first image of the shadow of black hole, we have models that predict a lot of rings, photon rings, the last stable ring for the matter, and so on. And all this will teach us a lot on how the black hole has formed, what is its spin, and what will be the future of the black hole. Now, for the future astronomy, it's even wider topics. I think that you will hear about dark matter with Simon White in a moment. But a big puzzle in astronomy is what are the dark sector, the dark matter and the dark energy. So we are knowing only 5% of the normal matter, and all the rest is unknown. So there will be a satellite launch next year by the European agency, Euclid. This satellite will detect 12 billions of galaxies at any distance from us, and it will be able to detect what is exactly the dark energy, because we don't know if it is constant or if it is a scalar field evolving with time. So this will give us a lot of information about the content of the universe. So we have a lot of mystery to solve in the future.
All right. Now, Professor, we still got one more question from the floor, if you don't mind us. There's one more question from the floor here. Okay. Please.
Good evening, Professor Komba. I have a question related to how the ejaculation of matters of black holes directly correlates to the universe expanding, and how it can be an explanation for dark matter. Does it have to do with the mention of the Doppler shift effect at the velocity of very high speed to show that matter is expanding even faster away from each other? Thank you.
Yes, there are several questions in your question. In fact, the black hole and the dark matter have nothing to do together. In fact, the black holes I've described here, the supermassive black hole, are each in their galaxy host, and they are formed from the normal matter. Why? Because the normal matter, the gas, radiates away its energy and can be dissipative and can concentrate in the center. The dark matter is not dissipative. It is not interacting with the photons. It's not radiating at all. So it cannot lose its energy, and it stays in a halo. So it cannot form black holes. So it's different object. And for the expansion of the universe, in fact, we know from now since 20 years that the expansion is accelerating. And that is the big problem of dark energy that has been invented to explain the acceleration of expansion. But it is not due to black holes. So there's no solution like that. We think that there is another element, the dark energy, which can have a repulsive effect. And if there was no dark energy, you have only gravity, which is only attractive. So you will decelerate expansion. If you want to accelerate expansion, then you have to have this fifth element, maybe, We know only 4 elements now, and there is a quintessence or 5th element that has to be discovered and to explain the acceleration of expansion.
All right, now, unfortunately, that's all we have time for this part of Q&A. And Professor Komba, thank you very much for your sharings and your time. We are definitely very lucky to have you with us at this seminar today. Have a good day. Merci beaucoup.
Thank you.
All right, now, our next presentation, may we invite Professor Chu Ming Chung, Professor of Department of Physics of the Chinese University of Hong Kong, to present to us.
Okay, good afternoon. I'm really happy to see so many secondary school students here. I got into physics because I was very active when I was a high school student, organizing an astronomy club. And part of my duty was to always learn something new so that I could teach the more junior students. Astronomy never stopped surprising me. There's always new stories. There are always new mysteries. And the beauty of the universe is always so attractive. So I never regret going into physics and astrophysics. Today I'm going to share with you a relatively new branch of astrophysics and cosmology, which has to do with neutrino. So maybe not all of you have heard about neutrinos, but we know that they are elementary particles. So they are part of the known matters. All known matters are made of these elementary particles. You must have heard of electrons. You might have heard of quarks. And we know that there are 3 types of neutrinos, being the elementary particles. Neutrinos are everywhere. So if you stick your hand out, every second, I estimated that there are about 10 trillion neutrinos passing through. Those are from the sun. Day and night. So daytime, they pass from above. At night, they pass from below. Neutrinos coming from the sun would penetrate the entire Earth non-stop. And they would penetrate you. So they're everywhere in this room. They fill the universe. If the Big Bang theory is correct, we believe that there should be about 300 neutrinos every centimeter cubed in the universe. These were produced in the first second of the Big Bang. So if you could detect these cosmological neutrinos, you would be receiving some signals from the first second of the Big Bang. And that would be tremendous. That's a really great achievement. We haven't been able to do that yet, but people are trying. So neutrinos are very interesting, but they are very difficult to work with. They interact very weakly. They do have weak interactions in gravity. But for example, if you want to stop a neutrino from the sun, you will need to stack Earth for 10 light years. And that's just pretty much impossible for us. And therefore, I'm going to show you some detectors which are huge. If you want to detect neutrinos, you need to construct huge detectors. Now, so why do we study neutrinos? Usually when you talk about astronomy, you think about telescopes, you want to watch the stars, you want to watch stars exploding, and so on. So those are all in the electromagnetic waves. However, more recently, we are believing that neutrinos might be the next important messengers. And maybe we can learn a lot about our universe from neutrinos. So let me just give you a very short list of why you should pay attention to neutrinos. So some of the most important outstanding problems in fundamental physics, in astrophysics and cosmology are related to neutrinos. For example, we have a standard model in particle physics. And now we know that neutrino would oscillate, would change from one flavor to another flavor. And because they have masses, just these facts already tell us that this standard model of particle physics is not complete. We must have the next level of theory. And neutrinos provide a lot of clues on how to go beyond this standard model. There has been a long-standing open question in cosmology and particle physics. How come our universe is dominated by matter? We see very, very little antimatter. And it's actually lucky for us that this is the case, because otherwise we would not even be here. But we don't understand why, where have all those antimatter gone? So this so-called matter-antimatter asymmetry is still an open problem. So you should try to work on it. And in the past 10 years or so, it has become more and more clear that neutrinos interactions would have this so-called CP violation. Basically, they would not be symmetric with respect to matter and antimatter. So that now it looks very promising that the answer to this question may lie in the neutrino sector. Now, we just heard about dark matter. So this is a big, big problem. How come a quarter of all known matters in the universe are unknown? This dark matter, what are they? So neutrinos are the only component of dark matter that's unknown. However, they must be a very minor component because they're very light. However, it's possible that there are more massive partners of the light neutrinos we know of. Sometimes we call those stereo neutrino, right-handed neutrino, and so on. And they are possible candidates. And it is also possible that dark matter would interact with neutrinos and so on. Now, I don't have time to go through all those particle physics, cosmology problems. Rather, I'd like to spend a little time to tell you about core collapse supernovae. This is how many stars die. Okay? Massive stars would die collapsing and then exploding. These are called supernovae. They're spectacular events. And now we know that neutrinos are of critical importance in such events. So I am very hopeful that neutrinos will become an important new astronomical messenger. And they will tell us much more about the universe that we might not even have thought about. So let me tell you a little bit about supernovae. So massive stars are much more massive than the sun. They would die as coarse collapsed supernovae. A supernova, typically, when the star blows up, is very, very bright. We're talking about 1 billion to 10 billion times the brightness of the sun. And the fireball would reach 10 to the 11 Kelvin. Very, very hot. When a star dies as a supernova, roughly 10% of its mass would be turned into neutrinos. So just thinking about that is mind-boggling. And the neutrinos will carry away more than 99% of the energy of this explosion. Right? So we see this bright fireball, but we see them in light. And light is an almost negligible component of the energy. If we could see a supernova in neutrinos, that would be really spectacular. Supernova neutrinos have been observed in 1987. So it has already become an observational tool. So this is supernova 1987, called SN1 1987A, after it blew up. Okay? So this is about as bright as 1 billion stars. But it remains so bright only for a few days. Okay? When this star exploded, 3 neutrino detectors on Earth picked up a burst of neutrinos that's shown here. And so we can triangulate the 3 detectors, we can correlate them in time and so on. They all point towards this SN 1987A. So we're pretty sure that these neutrinos come from that particular supernova. So a very simplified version of what a core collapse supernova is the following. So a massive star evolves until the core of it becomes all iron. And you can no longer extract energy from an iron core. So no more fusion, cannot resist gravity. The core begins to collapse under its own gravity. We call it gravitational collapse. This is actually quite spectacular. So imagine a stellar core, maybe a few solar mass, originally maybe 10,000 kilometers. Within a fraction of a second, it collapsed all the way down to maybe 100 kilometers. And during this process, the electrons and protons in the stellar core would be squeezed together. They merge to form neutrons and neutrinos. So by the end of this fraction of a second, the stellar core becomes mostly neutron, a very dense core of neutrons, and it emits a huge burst of neutrinos. So this core may become a neutron star or a black hole. So that's the birth of a stellar mass black hole. Now, when the core becomes mostly neutron has a very strong repulsive force towards each other, and then the core would eject a bounce shock. This shock would propagate out, and originally, we thought that this shock might be able to explode the star, okay? But no. Many people try many simulations. The shock propagates a little bit, and then just stop there. And then later, people found that in computer simulation, that the neutrinos that were emitted in the beginning, they carry a lot of energy. So a small fraction of them deposit the energy at the shock and revive the shock and exploded the star. So this is pretty much the standard scenario we have about core collapse supernovae, about how stars will explode. Okay? We're not sure yet that this is really the correct theory. This is just one possible model. Okay? So something as important as how a star die and explode, we still don't know. So there are lots of mysteries to be solved. That's why I love this field. This is a computer simulation I took from this group, performing a 3-dimensional simulation of how a stellar core would collapse and then explode. I just want to show you how complicated these calculations are. So I always tell my students that, oh, don't worry if you do astrophysics. You're so well trained in so many things, in computation, data analysis, science, logic, math, and so on. You would be in high demand for almost everything. Okay, so let me just spend a minute to tell you a recent work that we have performed relating to this issue. So for a long time, we like to search for quarks. Quarks are supposed to be elementary particles that make up neutrons and protons. Okay? So they're locked up inside neutrons and protons. Nobody has seen a free quark yet. However, in the theory of strong interaction, we also know that when these quarks and gluons, they get very close to each other, the interaction becomes very weak. Right? They don't interact when they're very close together. And therefore, it is quite possible that if you squeeze matter hard enough, or you heat it up to high enough temperature, so that the quarks and gluons are very close together, then they no longer interact strongly, and then they might be freed up. We call it deconfinement. Okay? So maybe there is a phase transition, just like water to air to gas, phase transition. At high enough temperature or density, you could turn ordinary matter into something we call quark-gluon plasma, a new phase of matter. So how high a temperature you need? 10 to the 12 Kelvin. Now, you probably have no feeling for this temperature, right? The core of the sun is about 15 million Kelvin, so that's way too cold. That's just nothing, okay? Now, I have a phase diagram here. On the vertical axis is the temperature. Tc is this 10 to the 12 Kelvin. So if you want to free up the quarks and gluons, you need to go above that if you go along the vertical axis. Okay? However, there's also a horizontal axis, which is density. So if you go to high enough density, you could also reach the quark matter phase. And maybe that's called collapsed supernovae. Just go along this blue line, not too high in temperature, but pretty high in density, so that we could reach that phase. And we call it a quark star. So maybe at the core of a core collapse supernova, we form a quark star. Okay? So recently, so just last year, we published a paper predicting what would happen if that's the case. Okay? I won't go into detail here, but in this simulation of a core collapse to quark star, we see first the original collapse to form the neutron core, and then a second collapse to form a quark star. And the second collapse would trigger a much stronger shock, and that would be able to blow up the star as well. So we don't even need the neutrino revival. This is a simulation done by my previous PhD student, indicating how a supernova may collapse to a quark star. Again, I just want to show you how beautiful this is. So sometimes I feel like we're playing God. We can change the physics inside a star, we can do crazy things and create new crazy objects, right? We don't know whether quark stars exist. We don't know whether there would be such quark matter inside supernova. But what we can do is to predict what you will see. So we can predict the neutrino signals. Okay? So there will be two bursts of neutrinos separated by a fraction of a second. So the future neutrino detector, they might be able to see these two bursts. The second burst is as strong as the first one. And we could also predict the gravitational wave signal. If there is this formation of quark star, after the second burst, the gravitational wave signal will be even stronger than the first collapse. So these are some predictions. Who knows? Maybe we're wrong. Maybe there's no such thing. But it's fun to make such prediction, and maybe 10 years later, if they really observe this, I would be really, really happy. So, by the way, I believe that we're entering a golden age of supernova physics. With large telescopes, large neutrino telescope. The one down here called Juno is very close to us. It's in Zhangmen. It's being constructed, a huge neutrino detector. So there will be a neutrino telescope very close to Hong Kong. The one above, Super K, is in Japan. And then we have also gravitational wave detectors. So when we have the next supernova and we observe them in all these different detectors, we'll know much more about supernova. Okay, I'm going to skip the next part and just give you a quick summary. Neutrinos are very important. We believe that they make core collapse supernovae possible. And supernovae themselves are important for stellar evolution, spreading of elements, and our existence. I believe that there will be an upcoming revolution in supernova physics. There'll be many different observations in different wavelengths, different messengers. And hopefully we can learn much more about how stars die, how they explode, and so on. So I'll just stop here. Thank you very much.
Thank you. Wow. It's amazing how much we know about the universe and also how much we don't know, isn't it, Professor? All right, now we're in the Q&A part now. Shall we take the first question from online first, Professor?
Yeah, sure.
Okay, the first question is, we heard that Daya Bay in Hong Kong is the best site in the world to study neutrino. What do you think about that?
Yes, indeed, I think we are very, very fortunate. So about 15 years ago, a friend of mine who's a professor at Berkeley at that time, he's also from Hong Kong. He came to Hong Kong and talked to me. He told me that, Ming Zhong, do you know? Daya Bay is the best site in the world to study neutrinos. Why? First of all, there are 6 reactor cores in Daya Bay. So it is one of the top 5 reactors in the world. Now, the more powerful a nuclear reactor is, the more neutrinos it generates. Okay, so there's huge amounts of neutrinos generated every second from Daya Bay, and they are all for free. Okay? Another reason why Daya Bay is good, there's a mountain, pretty tall mountain, right next to the nuclear power plant. And for neutrino physics, because I told you that they don't interact much, so our detectors must be shielded from environmental radiation, cosmic rays, and so on. Cosmic rays are a big enemy. So with a tall mountain, we just have to build a tunnel into the mountain, build our labs inside there, and then we have a very, very quiet environment to study these neutrinos. And I said that we were very fortunate because it turned out to be a very successful experiment. We measure a new channel of how neutrinos transform from one flavor to another one. And it also gave us, in Hong Kong, a big boost in joining and doing fundamental physics. It was really a memorable experience for myself.
Fantastic. All right. Now, the second question from the floor here, our live audience. Yes, we already got a student here, and on the 5th row here. That's right.
Thank you for your sharing. Do we know why stars die at this point?
Yeah, we know to some extent, okay? So we know that stars are supported by the energy generated by nuclear fusion at their cores. And the nuclear fusion would fuse lighter elements and heavy elements, but when you reach iron, so when the stellar core is all iron, then you can no longer extract energy through fusion of ions, okay? So at that point, you cannot generate more energy, no thermal energy, then gravity would win. So that is basically how massive stars would die.
Very interesting. Well, you learn something new every day, don't you? All right. Because of time limitation, that's all the time we have for Q&A this time. Okay. Thank you very much, Dr. Chu, or Professor Chu. Great to have you with us. Please have a seat, and we'll have you back for our panel discussion a bit later. Okay. All right. For the next presentation, we're very excited to have our 2017 Shaw Laureate in Astronomy, Professor Simon White, joining us live from Berlin. Professor White is an emeritus director of the Max Planck Institute for Astrophysics. So ladies and gentlemen, let's welcome Professor White. Hello, Professor White.
Hello.
How are you today?
I'm very good. It's very nice to be here, at least in virtual form.
Well, you look good from our side. All right, now we've been all waiting for you, and the time is yours. Please take it away.
Hello. Well, today I would like to show you what I think has a good claim to the most extraordinary picture in all of science. But to explain what this picture is and why I think it's so remarkable, I have to start with something you all recognize. So I suspect most of you in the audience recognize the picture I have on the screen at the moment. This is, of course, a picture of the whole of our world, and it was made by satellites circling above the surface of the world, above the Earth, a few hundred kilometers above the surface, with cameras facing down and photographing the surface, and then all these photographs were pieced together, and we get a map of the whole surface of the world. Now, if you imagine the cameras on these satellites were turned upwards and looked out instead of down, then we'd get a picture which looks like this one. And this is a picture of the whole sky as seen from the Earth outside the atmosphere. And what we see, of course, are the stars. And right down the middle of this picture, you see a big band, which are the stars of our own Milky Way, our own galaxy. And there are very many of them, and they're in a kind of disk, which is why it looks like a band on the sky. And we see stars at different distances. And in fact, even in this image, the most distant stars are about 10,000 light years away, which means the light from those stars has taken 10,000 years to reach us. So in other words, when the light left those stars, they were still before the beginning of recorded history here on Earth. Now, our galaxy, it turns out, is just one of many. So here is our biggest neighbor galaxy, the Andromeda Nebula. You can actually see this from Hong Kong with your own eyes. You don't even need a telescope. You just have to go somewhere where it's dark and where the sky is clear. And then if you know where to look, you can see the Andromeda Nebula, as long as your eyes are good enough, on a dark night. And this is much further away. In fact, the Andromeda Nebula is about 2 million light years away from us, which means the light has taken 2 million years to get here. So when you see it, you see the nebula not as it is today, but as it was 2 million years ago. That's to say, before there were any human beings on the Earth at all. Now, the Andromeda Nebula is just one of many galaxies. If you map the whole sky again, you can make a map of the galaxies across the whole sky. So again, this is a whole sky map, but now every dot on this map is an individual galaxy like the Andromeda Nebula. And there are about 1 million of them on this map. And you can see they're not distributed uniformly over the sky. There are galaxies in all directions, but in some directions there are more than in others. And this is what's known as the large-scale structure of the universe. The galaxies are arranged in big structures throughout space. And the most distant galaxies in this map are about 1 billion light years away, which means the galaxies that you see are not the galaxies as they are today, but as they were 1 billion years ago. That is before there were any vertebrate life in the oceans and no life on land at all on the Earth. So we're seeing already 1 billion years into the past. But with a better telescope, we can actually see even further. So here's a picture taken with the Hubble Space Telescope, the most successful perhaps of all the telescopes in space, which takes images in optical light with a camera. And if you point that camera in this one direction and just keep the exposure going for 300 hours, then you get a picture like this one. And this picture is a tiny fraction of the size of the full moon. But you can see the image is full of galaxies, and some of them even look quite like the Andromeda Nebula. But these galaxies are much further away. In fact, the most distant galaxies here, which are tiny specks, not the brighter ones that you see, are so far away that the light from them has taken 90% of the entire age of the universe since the Big Bang to reach us. So we see these galaxies not as they are today, but as they were when the universe was 1/10 of its present age. So that's well before the Earth and the Sun had even formed. So we're seeing back in time a very long way. And these galaxies today are actually 30 billion light years away. They were much closer when the light left, but since then the universe has expanded. So today they're further away than they were back then. So we can ask ourselves, how far back can we see? How far can this seeing into history be pushed? And the answer is much, much farther, but you have to look in a different kind of light. You have to look not in optical light, like the pictures I've been showing you so far, but in microwaves. So in 1989, NASA launched this satellite called the COBE satellite, which went into space and mapped the whole sky in the microwaves. And as you can see, it was in an orbit just above the surface of the Earth, and it went round, and it kept looking away from the Earth for a long period of time until it had made a map of the whole sky in microwaves. So this is a wavelength of about 1 millimeter, similar to the microwaves in your microwave oven. So after 4 years of observing, the scientists could finally make a map of the whole sky in the microwaves and see what it looked like in this new wavelength. And their picture looked like this. This is COBE's map of the whole sky. The color represents the temperature. And the average temperature of the sky as measured by COBE is 2.728 degrees above absolute zero. And that's the orange color. And the contrast in this map is 1/10 of a degree. So the points in the map which are red are 2.83 degrees above zero, and the points which are blue are cooler, 2.63 degrees above zero. But as you can see, there are no blue or red points. It's all orange. And that's because COBE found the whole sky to be very nearly the same temperature, 2.73 degrees. To see any structure at all, you have to increase the contrast dramatically. So here is the contrast enhanced by almost a factor of 1,000. So now you actually see something. You see that one side of the sky is hot, orange here, and the other side of the sky is cold, it's blue. And the differences from the average temperature about 1 part in 1,000. And what that is a measurement of how fast our universe is, our Earth is moving with respect to the whole of the universe. We're moving in the direction towards the orange patch. And because we're moving in that direction, it looks a little bit hotter by 1 part in 1,000. And we're moving away from the point where it's dark blue, that's colder by 1 part in 1,000. And we're moving at 1,000th of the speed of light. That's about 300 kilometers every second towards the orange direction. So if you look at this very closely, this motion is not the only thing in the picture. There's something else along the equator. So if we subtract the pattern that we see that comes from our motion and amplify what's left by another factor of 100, we get this picture. And this picture now has a contrast where the differences between the red and the blue, away from the middle here, those differences are about 1 part in 100,000. So now you can see there's something across the middle, and that's actually microwaves coming from the material between the stars in our own galaxy. And that's not what I want to talk about now. What I want to talk about is what we see when we look away from the Milky Way, up to, out of our galaxy. We see that so to see this better, you need a better telescope. And 20 years after COBE, the European Space Agency launched the Planck satellite. Because they wanted to measure very precise temperature differences, they sent it a long way away from the Earth. They sent it to a place called Lagrange Point 2, L2, which is, to think where this is, you imagine taking a line from the sun through the center of the Earth, continuing it out the other side, out past the orbit of the moon. Eventually you come to a point where you can send a satellite and it will just sit there and go round, following the Earth around the sun and staying at that point. And that's what's known as the Lagrange point. And the reason to put the satellite so far away is then you can point away from the Earth and the sun and the moon, so all the things which can cause temperature fluctuations in your instruments are behind you, and you can measure things very precisely. And after a few years, Planck also had made its own map of the sky, and it looks like this. So this is the map of the Planck sky. Because Planck observed several frequencies, they could take away the emission which came from our own Milky Way, and what you see now is the emission which is coming purely from further away, from something else. And this is the image that I want to focus on, because what we're seeing here is an image of the edge of our entire observable universe. Let me say that again. This is an image of the boundary of our whole observable universe. And in fact, this image is now so precise that parts of this have been mapped with other instruments since then, and they reproduce all these little features that you see. And remember, this are very small features. The red points in this picture are just a few parts in 100,000 warmer, and the blue parts are just a few parts in 100,000 cooler. But nevertheless, there are differences. So to explain why this is so extraordinary, I need to explain to you what you're actually seeing here. So the first question, of course, is where is this structure? So I think the best analogy here is, I don't know what your weather is like in Hong Kong at the moment, but here in Berlin, it's pretty cloudy. And as a result, when you look up, the sky looks gray. What are we seeing? Well, of course, we're seeing the clouds. The air beneath the clouds is transparent, but the clouds scatter light. So when we look up, we see the clouds. And so when we look at these clouds, it's gray, but it's not completely gray. In some places, it's darker than others, and that is structure in the clouds. So when we look up today, we see structure in the clouds. So the microwaves, it's the same thing. Today's universe, and in fact the universe over most of its history, is transparent to microwaves. We just see through it. But if you go back far enough in time and space, the universe is no longer transparent, and there's a surface of clouds. And light, ordinary electromagnetic radiation, doesn't pass beyond those clouds. So that's the edge of what can be seen in light, and so that's why I call it the edge of the visible universe. And that's what we're seeing, and that's where the structure is. So what are we seeing? What is this structure? It's small variations in temperature, and those are caused by sound waves. In ordinary air, like in the room where I am and where you are, sound waves are tiny fluctuations in the density, pressure, and temperature of the air. And what we're seeing in the microwave background are small fluctuations in the temperature and density of those clouds. So it's directly analogous to the sound in the room. If we ask, how far back are we seeing? At what epoch are we seeing this structure? Well, the universe was last opaque, was stopped being transparent, just 400 years after the Big Bang. So we're saying all the way back until just 400,000 years after the Big Bang. And at that time, the universe was 1,000 times smaller and 1,000 times hotter than it is today. So although the clouds are 3 degrees above absolute zero as we see them today, at that time, their temperature was 3,000 degrees. So similar to the surface of the temperature of the surface of the sun. So we're seeing structure in the universe on the whole of its visible boundary at a time when it was 1,000 times smaller and 1,000 times hotter than it is now. And this structure is in the form of very weak sound waves. No stars, no galaxies, no planets, no rocks, no people, just weak sound waves. So we can ask, when do we think this was created? We think it was created just a tiny fraction of the second after the Big Bang. And if we ask, what has it become? Well, structure grows through gravity. We think everything in the present universe, all the stars, the galaxies, the planets, the people, they were all formed from this structure. So we're seeing the predecessors of everything that we know around us. Galaxies, stars, planets, and people. So how do we measure things? Well, just as if you hear sound in a room, you can break it down into different frequencies and ask how loud are the oboes playing, how loud are the double basses playing, how loud are the violins playing. You can do the same for the sound waves in this cloud, and that's what's shown in this graph, which is the only technical plot I'm going to show you in this talk. And what's shown on the horizontal axis here is the frequency. So long waves, low frequencies, the double basses, if you like, are on the left. Short waves, high frequencies, the piccolo, if you like, is on the right. And what's plotted vertically is the loudness or the amplitude of these waves as measured directly from the map. And the little red points are the direct measurements from the map that I showed you. And you can see that they're very well measured, But over most of this range, they have very small uncertainties. The uncertainty in average value is shown by the vertical bar on each little red point. And except at the lowest frequencies, you can see they're very small. Now, what's shown in the green curve is a theoretical prediction for what this ought to look like based on the properties of the universe at this time. And it was very simple. It was nearly smooth with only sound waves. And these properties depend on three aspects of what happened in the earlier universe. They depend on the geometry of the universe, because that changes angles on the sky into centimeters or light years in the clouds. It depends on what the universe was made of at that time, because that determines how waves propagate, just as the nature of the gas in which sound waves propagate changes the properties of the sound. And of course, it depends on what actually created these waves even earlier, before that time. So if we ask what we've learned from the microwave background, the geometry turns out to be very simple. It's kind of the natural geometry which you know from geometry in school, where parallel lines never meet. The angles of triangles always add up to 180 degrees. This is what's called flat geometry. For what it's made of, it turns out that only a small fraction is made of ordinary matter, like stars and people and planets, roughly 5%. Much more, 5 times as much, in fact, is made of something else which interacts with ordinary matter only through gravity and not through electromagnetic radiation or any other kind of force. And the rest is something else, some new kind of energy, so-called dark energy. It seems to, we don't know where it comes from, we don't really know what it is, but we do know that it's causing the expansion of our universe today to accelerate with time, as was discovered about 20 years ago. And on the final aspect of what caused the structure, the properties of these fluctuations are just what it would be expected if all cosmic structure was due just to quantum fluctuations in the vacuum itself at a very early time, maybe just 10 to the minus 30 seconds after the Big Bang. So this is an extraordinary idea. If this is correct, and it's consistent with what we see, then it says that the sound waves were formed just as properties of the vacuum at very early times in quantum mechanics. And they then turned into everything. So that means everything around us, all of us, and everything we know, is a consequence of the properties of the vacuum at a very early time. So how can we test whether this idea really is consistent with what we see around us? Well, if it's correct, then we know the properties of the universe very well at this very early time. So we can ask a computer, if you start with these properties at this time, what should happen later? So we can put the equations which describe the evolution of the universe into a computer. Mostly it's just gravity, so that's relatively simple. We can give initial conditions, which are the ones we actually see, and we can go forwards and ask whether we can then explain today's universe. If I can get the slide to move. Up, I'll jump one. So if we do this, this shows the result of such a calculation, where we started with the initial conditions predicted by the microwave background, and we asked the computer to calculate what the distribution of dark matter would look like in the universe today. And this is a very large region of the universe, and it shows the dark matter today is predicted to be in clumps, which are arranged in large structures. So now we want to compare this with what we see. So we have to populate this dark matter with galaxies. So we have to make a model also for how the stars and galaxies formed. And if you do that, we get the next picture, which looks like this. And this is a picture of what the light is predicted to be in today's universe. So now we can actually compare this directly with the observed universe. And that's what's shown next. So here, the plots at the top and on the left, which are in blue, are plots of the distribution of galaxies in the real universe. So every dot in each of these plots is an individual galaxy. You have to imagine that we are at the point towards the center of each of these wedges, and we're looking out at all the galaxies in a strip along the sky, and the point is put away from the vertex of the wedge at the distance that the real galaxy is measured to be. And so what you see in these wedges is the distribution of real galaxies today in our nearby universe. Now on the right and below, you see similar wedges where a virtual student has been sent with a virtual telescope inside the computer calculation and asked to observe the simulated universe in the same way as the real one, and you can see the pictures that were made. And what you can see is the statistical properties of the structures look very similar. So this shows that by just using the laws of physics, mostly gravity, to integrate forwards from 400,000 years after the Big Bang to today, we can actually reproduce the large-scale structure of the universe. And although I don't have time to go into this today, in fact, each of these points is not, of course, just a point. It's a galaxy like our own Milky Way or the Andromeda Nebula or one of these galaxies I've shown you here. And in fact, computer simulations have been able to show that starting from the initial conditions at these very early times and integrating forwards, you can understand many of the properties, not just of the large-scale distribution of galaxies, like in the background plot, but even of their internal structure, as you see in these other pictures. So in this way, we are able to start with a picture that we have of the very early universe and understand how it developed into the universe today. And as you can imagine, galaxies are very complicated things, so there are very many parts of this story, of the details, which are still not clear. But I think it's nevertheless remarkable that we actually see the initial conditions for the formation of everything directly in front of us on the sky. So I'll stop there.
Thank you very much, Professor White. That was amazing. Thank you so much for all the great information you've given us. And I'm sure that would have inspired a lot of our viewers to think deeper. And I'm sure that a lot of questions are coming in as well. Professor, it's time for Q&A now. Shall we take the first question from online? Okay, the first question is, Professor, even if we observe CMB, does it mean that we still cannot get a full view of the whole universe? That's the first question.
So what we see in the CMB is the edge of the universe. And anything between us and them, so anything and this cloud surface, anything at later times, let's say after 400,000 years after the Big Bang, will emit light, and we should be able to see light from it. So in principle, with telescopes, we should be able eventually to observe anything which is in front of the clouds. But anything which is behind those clouds will be hidden from us, at least in ordinary light. Perhaps if we could see the neutrinos, we could see further. Or the gravitational waves, we could see even further. But in ordinary light, we cannot see past the clouds.
Okay, direct and easy. Okay, next question we're gonna take from the floor here, from a live audience. Can we pass the microphone to this gentleman here wearing red?
I have one question about the large-scale structure. I remember seeing recently that there are some researchers saying that there are structures that are too large predicted by the theory. I think it was about some quasar groups and other stuffs. My memory is not very clear, but I remember there are some researchers saying that there are structures that are too large, and I want to know your opinion about this.
Yes, people, of course, are always trying to find holes in this picture, because it's very nice to have this story and be presented something, we found the answer, that's the way it is. But science works by picking holes in what other people think and finding the things that don't quite work out. So things like these very large structures, people keep looking for them to try and understand, is this really in conflict with what's predicted or not? And often the difficulty is to make a properly valid statistical comparison between something you picked up and suddenly struck you as looking strange for some reason, and what will be predicted in reality. So I think the current situation is for large-scale structures in the universe, there isn't really anything which appears to be larger than is predicted by the theory in a quantifiable way. That is, so at the moment, at least on large scales, there don't appear to be any major discrepancies in, say, finding a bigger cluster than ought to exist, or a bigger group of quasars.
Fantastic. There you go. Your answer, your question is getting answered by one of the greatest scientists in astronomy. How great is that? All right. Now, because of time limitation, we can only take 2 questions for the time being. But keep your questions because we still have a panel discussion, and you still have chance to ask later on. Okay. Thank you very much, Professor White. Please stay with us because we're going to invite you back very soon for panel discussion.
Okay. Thank you very much. I'll see you in a minute.
Okay. Thank you. All right. I'm gonna move to this part of the stage because our lovely staff will help us arrange the stage for panel discussion. Now, for the time being, I want to share something that I learned recently from a documentary I saw not long ago. Do you guys know that the moon is actually not round shape? Do you know that? It's actually not round shape. Someone just nods her head. Okay, so only me who doesn't know. Okay, fine. Well, it's actually, I learned that the moon is actually lemon-shaped because it's got bulges at both ends. Isn't that very interesting? So, and also a friend of mine who study in astronomy, he says that, you doctors do your research in the lab, whereas us who study astronomy, the universe, the whole universe is our lab. So I got nothing to say to that. I said, okay, you win. So, the universe, there's still a lot for us to learn. As I said before, it's amazing that how much we know about the universe now, but also how much we don't know. So there's still a lot of chance for you to explore a lot more. Okay, now it's time for our panel discussion. We will invite first our moderator, Professor Yang, to the stage to help us moderate this panel discussion. And also, we would like to invite Professor Chu to the stage to join us. And of course, we have Professor White joining us online from Berlin. Okay. Have we got everyone on stage now? Oh, yes. Fantastic. All right, just a reminder, after the panel discussion, there's still Q&A session, so you guys can still ask questions if you want. And online friends, you can still submit your question online too. Okay, and now I shall pass the time to you.
Thank you.
Thank you.
Hello, Professor White. Nice to see you on screen and in 3 dimensions.
Nice to see you too.
Yeah. So this is a bit precarious, these seats. Okay, perhaps I could start with one question. And I was just discussing with Professor Ju earlier this afternoon. I was actually struck thinking back to a time when I was about the age of, maybe a bit older than most people in the audience. I was learning all kinds of stuff which now turn out to be wrong. For example, we were told almost as a matter of course that neutrinos had no mass, that black holes are formed only from the collapse of stars, that the expansion of the universe was decelerating. The only question was how big was the deceleration. So my question is to both of you, how should young people strike a balance between learning the orthodoxy from old people like us, and between that and a spirit of skepticism, being prepared for the possibility, in fact, the likelihood that much of what, or at least part of what we have heard today will turn out to be wrong, say 20, 30, 40 years from now. Who would want to pick that up first, if that question makes sense?
No, I think the question makes sense. Should I start?
Please.
I mean, I think to make progress, you have to pick holes in what we know. And so you have to be skeptical of it. But of course, you do need to understand what we know and how we know it. So it is important to learn, I wouldn't say to learn the orthodoxy, but to learn what the evidence is and why people have come to this conclusion. And then the way to question it is to think, well, I can see why they might come to this conclusion based on this evidence. You know, is this the only possibility? If this is true, what else would it imply? And by thinking about exactly how the logic works, and whether there are other alternatives, and whether perhaps there are different ways to get to the same set of observations, and trying not necessarily to follow the same path as people did previously. That way you can find a way, a new angle, which perhaps can lead to a new insight.
MC?
Okay, let me, maybe I take it from a slightly different angle. I grew up in Hong Kong. I did my high school in Hong Kong, and then I went to the States for college. I think many of us who were educated in Hong Kong are always almost too conservative. So we're trained to do the exam questions correct. So there's always an absolute correct answer. You don't want to miss a point, right? Such training is useful. It's very solid training. But sometimes it also forbids us from thinking bravely, being creative, and trying crazy ideas. Okay? That's something I learned when I went to Caltech as an undergraduate. I think people, at least in Caltech, I think generally they respect crazy ideas, even though most of them are wrong. Okay? So that's something I always like to instill in my students, that be crazy, okay? But still, do your exam right, okay? I don't know how to strike a balance, but I think at least the awareness that crazy ideas are good, I think that is also important. So don't be afraid to be wrong. I guess that's my main message.
We have
I think I agree with that.
Yeah. Thank you. We have quite a number of questions posted online. Let me just pick one, which seems to me to be quite interesting. The question, as I read it, goes as follows, and I will amplify it. The question is, what kind of technology or software do astrophysicists use nowadays in the field? And I would amplify that in the following way, that given the present level of technology at any one time, some problems are not doable. Some problems are already trivial, has already been done. So the follow-on question is, how do you have developed the kind of taste that will steer you towards the type of problems that's just on the edge of being doable? And that's probably where the biggest rewards are. How would you agree with that statement, and how would you develop that kind of taste? Simon, perhaps you first.
Well, if you look over my career, for example, the power of telescopes, and the biggest telescope in the world was 5 meters in diameter when I was a young student, and it's soon will be 30 meters in diameter. So that's an increase of a factor of 6 in diameter, or a factor of 36 in collecting area, which is substantial, but not so huge. And the best detectors used to be photographic plates, and now they're all electronic. That's about a factor of a few hundred in sensitivity. So that's also quite big, but not huge. On the other hand, the improvement in the speed of computers has been tens of millions, and the size of computer memories has also increased by tens of millions. So our computational abilities have actually increased by much larger factors, over my career at least, than our observational capabilities, although both have increased. So I think that was, of course, good for me as a computational astrophysicist. But to come to the real question, I think you should always follow what you find interesting. You should do what you like. I mean, I became fascinated by what was called the missing matter, which now we call dark matter when I was a graduate student. How is it we could seem to not understand the distribution and properties of the dominant component of matter in the universe? And I followed that and find ways to answer it. And then that led to things like the cold dark matter model and our current views on what dark matter might be. I think the important thing is to find something which you find fascinating and then try to figure out how to use the technological means which you have available to address that. I don't think you should start from the technological means.
Yeah, I completely agree. So usually it's the problem that are interesting enough that get you intrigued and you really want to think about it. Technological issues come secondary, I think. But I do want to emphasize another point that I think our students in Hong Kong are relatively weak. I find it extremely useful when I talk to people in different fields, different countries, different culture, and that is extremely important to stimulate ideas and the realization of what are possible, what are interesting problems even, right? So if you just lock up your door and work on your own problem, you might not develop the taste, as you put it, to be aware of the cutting-edge problems that are just beginning to be solvable, and you will get there first. So that's very important, to communicate, to exchange ideas, so don't be shy.
I can confirm that Professor Ju's office door is always open. You walk down the corridor, his door is open. You can pop your head in any time.
Yes.
I have a question. Yeah, Simon.
Yeah, I just wanted to reinforce that. I think communication is critically important. And, astronomy is a science about the whole universe, and it's a global science. And in principle, although there are parts of it which are applicable to more social issues or to more technological issues in today's world, most of it is finding out about basic physics and astrophysics of how the world works. And this should be an international subject. And in my experiences, we always make progress by talking to other people about it, because talking to them, you find out what they're thinking about, and also it stimulates the competitive parts of our nature that we want to go and show, that we can do as well as they are doing, or we can do better than they did. And constructive competition is very important. And so I think sometimes in today's world, this is becoming less easy. It's becoming...
Yeah, in fact, I have a question here that addresses precisely that point. How do you usually find new collaborators, especially those in fields different from your own? Any takers on that question? How do you find collaborators, or even just people to talk to, interesting people to talk to, in a way that is not perhaps necessarily so focused on trying to solve a problem, just talking, chatting?
Just go to coffee often.
What?
Just go to coffee often.
Yes.
Or tea.
Go to coffee and tea often, yeah. In fact, I was just relating to Professor Ju earlier this afternoon. I recall in my undergraduate days, I had Kip Thorne teaching me about black holes and implying more or less that black holes would be formed upon stellar collapse only. And then I was also hearing Martin Schmidt talking about quasi-stellar objects. And somehow those two ideas never met at that time, even though Caltech was a very small place. Everybody knew everybody else, had coffee all the time. So perhaps we need even more of that. So perhaps I can open to some questions from the floor here.
Hi, good evening, Professor Young, Professor Chu, and Professor White. I have a question on encouraging young students like us on on going on the path of science and research. So do you have any advice or any words of encouragement for people like us to continue sciences? And what are some of the life experiences you have gained throughout your experience in science? Thank you.
Yeah, so first I will start by saying that over the past 20 years or so, I've seen many breakthroughs. I did not think that they were all possible. So I was actually telling Kenneth that when I went to Caltech in 1980, I visited the LIGO 4-meter prototype. That was 1980.
Hello?
Oh, now we hear him. And then we really detected gravitational waves and all these wonderful black hole mergers, neutron star mergers, maybe even more exotic objects over the past few years. So many things are happening now. I also remember when I went to Caltech, I hear people searching for Higgs, measuring neutrino oscillations. Those were long-term projects. And for many years, people were very, very hard. And somehow they all got results. They all got breakthroughs in the past 10 years or so. So I truly believe that this is the right time to do research. There are many new discoveries waiting for you. The universe is much more wonderful than we could imagine. So a lot of things are waiting for you. I think that's the biggest encouragement I can give you. If I told you that, oh, almost everything is discovered, we understand everything, then forget it. Right.
So I think you have to follow your own interests and your own feeling of what you like and what you think you're good at. And you should not focus on what you think other people will like, but on what you find interesting. And you should also, of course, focus on what you think you're good at. And you should always have confidence in yourself, not that you're right, because very often you'll be wrong, but confidence that you can learn and you'll figure it out. And I think if you have that drive that you want to know and you want to find out, then you can push yourself to do the research and you can find the way. And the way to find the correct way is often to talk to other people, to understand how other people have looked at the problem, to think about how you might have done it or what you would have done differently, to think how perhaps it might be done better. But always follow what you want to do.
Thank you. Yeah. There must be more questions from the floor. Please raise your hands. I'm afraid, you know, that the light is in my eyes, so I can't see very well with the floor. Okay, please, over here.
Good evening, professors, again. So about a telescope called the Webb telescope that is going to come up very soon. I'm sure a lot of people are quite excited about it. So I just want to ask, what can we expect from this telescope? Because it detects the infrared radiations from the universe. So what can we expect from it? And when we were to enter the astrophysics field, what can we study about the result of this telescope gives? Yeah, thank you.
Professor White, you want to respond to that?
Yes, I think, well, it should be launched very soon. So, of course, we're all waiting and keeping our fingers crossed that everything will work perfectly and it will soon be observing for us. So I think it may well turn out the most exciting things from the Webb telescope are not in any of the fields that we've heard about today, but rather in studying planets around stars other than our own. Because by using its sensitivity and its wavelength coverage, it may be possible even to study the atmospheres of planets orbiting around other stars. And so we might learn whether planets around other stars have atmospheres which might perhaps have life. I mean, if you're very optimistic, you can imagine they might even find some evidences in the chemical composition of the atmosphere that indicate the possible activity of life on their surfaces. So I think that is one of the most exciting things that we can hope for from Webb. In my own field, I think we hope to see further back in time than the galaxies we've seen so far, and to see the very first events of star formation in the very first galaxies, which will happen even further in the past than the Hubble Space Telescope pictures that I see you. So I think Webb should also be able to push to see things at even earlier times and see how the formation of the galaxies actually began.
Yeah, somewhere in the middle there. Yeah.
Good evening. May I ask, did anyone inspire you to pursue your astrophysics career? And also, did you ever face challenges or even wanted to give up on your research? If so, what made you determined to keep on doing it? Thank you.
Yes, before the two of you answer, I actually have two similar questions submitted online. Let me perhaps cite those as well. One is, let me see now. What do you find most rewarding in your work, which is not understood by the masses and takes years of dedication to literally find a needle in a haystack? Lots of work, decades to that maybe echo the challenges that were mentioned. And the other question concerns whether a career in astrophysics and in science in general involves sacrifices because of the long period of dedication. So I think those are just one cluster of very similar questions. Simon, you want to come first?
Okay. Well, I think in terms of what inspired me, I was actually most inspired by some of the professors I had when I was a student. And what inspired me was less the actual subject matter that they were working on, although of course I found that interesting, but their enthusiasm for what they were doing. And one of the persons who taught me when I was a student in Cambridge was a man called Donald Lindenbell, who was actually one of the first people who suggested that massive black holes might in fact power the quasars that we heard about from Professor Chu just a few minutes ago. And he just had extraordinary enthusiasm for his subject and for describing it in mathematics and for understanding how things worked. And this was very infectious. So that was one aspect. And challenges, there are always challenges in trying to answer problems. In terms of personal challenges, you don't always get what you want. And at one stage, I wanted to keep working in Berkeley, in California, where I was. But when the job came up, I didn't get it, and I moved instead to somewhere else, to the middle of the desert in Arizona. And then later, when I became disillusioned with things in Arizona, I went back to England, and Cambridge, but that didn't in the end work out as I was hoping. And eventually, I decided it was time to move on and went to Germany, and I've been very happy there ever since. But in terms of the subject itself, I've always been interested in it. I've always wanted to find out how it works. So there, somehow, I never had doubts. And when other things weren't going well, I always believed that that the subject was interesting and I could actually contribute to finding the solution, and that helps you through.
MC?
Yeah, so again, let me try to answer that from the perspective of someone growing up in Hong Kong. Okay? So I, as I told you in my talk, I was inspired by being an organizer of the Astronomy Club, where organizing stargazing activities, telling stories to junior students, and therefore I had to read a lot. I read about relativity, read about Einstein's work, and so on. So those were the early inspiration for me. When I first got to Caltech, that was an experience that I could not forget. So not long after the school started, maybe around November 1980, suddenly I saw huge TV screens set up everywhere on campus. Okay? So those were not LCD, okay? Big things, right? And they show some very static picture. Turned out that Voyager was just arriving or going to fly by Saturn. So they were showing all this picture, Saturn and Titan and some other satellites. Okay? The entire campus, everybody was excited. I remember one day, the spaceship was to fly through the rings of Saturn. And everybody, I meant everybody, the secretaries, they had the lunchbox and just stare at the screen. Okay, so that was really so exciting. Everybody thought this is the most important, most exciting moment, right? So those were really inspirational. Sometimes it's difficult in Hong Kong when everybody thought that money is the most important, right? So I was lucky enough that I got into an environment that the pursuits of knowledge, of trying to solve mysteries, exploring new worlds, those are also very important. And you have to decide for yourself, of course, whether that excites you, whether you want to do that. I think once you make up your mind, you can really do something important. Everybody can. I truly believe that. Challenges, of course, always. And part of the frustration is that I always have to find money to support the research. And it's not always true that you got the grants you need. Okay, so you just have to keep working harder and harder and trying to convince people. Yeah, but looking back, I still think it's all worth it. I think it's truly exciting to be able to participate in this exploration of the universe. Yeah.
Other questions from the floor here?
Professors, it's an honor to meet you guys. I'd like to ask you a very simple question. What makes one a scientist? Is it a job title, or is it something that has to do with our thoughts and the way we perceive the universe, might I say? Thank you.
Well, scientist is not a job title, but anyway, please, Simon.
I think in the end it's curiosity. What really makes you a scientist is being curious about how some aspect of the world actually works and wanting to work it out for yourself. So having, I think, the best research, at least in astrophysics, is curiosity-driven. And I fully echo what Professor Chu was saying earlier, that one of the great advantages of astrophysics, unlike some other branches of science like mathematics or theoretical particle physics, is that we have so many wonderful images of galaxies or planets that people can relate to, that actually communicating with the world at large is not difficult. And that's one of the pleasures that makes astrophysics something special.
Yeah, I don't think I have anything to add, but I also like to echo this last statement. I often run into quote-unquote non-scientists. Okay, so for example, even the security guard in the science center in my university, sometimes he would just run into me and ask, "Oh, I saw this very bright star last evening. What is it?" Okay, so everybody is curious. I truly believe. Okay. Now that said, I think many people would stop at that. So they will not try to understand something new. Right? I think that's an important quality. You would pursue your interest, follow through your curiosity, try to understand it, try to solve the problem, even if sometimes it involves difficult mathematics, computing. You're not afraid of doing the experiments, doing the observations, doing the tedious work to follow through. I think those are also very important.
I would like to add just two remarks. Well, one is that this spirit of curiosity is, of course, not unique to astronomy and astrophysics. It permeates in slightly different ways many, if not all, aspects of science. So I think for a scientist, the spirit of curiosity would be enough. And the second point I want to make is curiosity sometimes would be satisfied in so-called aha moments. Sometimes you suddenly discover that, I suddenly understand something, even though it may not be novel in the whole world, but for you, it's the first time. That's a sense of great satisfaction, and even greater satisfaction if you are the first one to understand that particular problem, and that is what research is about. And that is the reward, if you like. Right, any more questions? Any more hands? I see one hand here. Yeah.
Good evening, professors. May I ask if all stars can be seen by naked eye? If not, what caused that to happen? Thank you.
I don't think we heard the last bit clearly. No?
Yeah. Can you repeat?
I heard.
If not, what caused that to happen?
Why couldn't we see all stars, right?
Yes. Well, let me answer that. It's actually relatively simple. It's just how bright they are. Our eyes are only sensitive to relatively bright objects. So if they get fainter or they get farther away, we can't see them any longer. It's like if you imagine a flashlight, if you shine it in your eyes at the end from your hand, you see it very easily. If it's at the bottom of the garden, you can still see it. If it's a kilometer away, you can maybe just see it. But if it's 10 kilometers away, you won't see anything. And that's just because, not because the flashlight itself isn't just as bright, but it's because it's too far away, and the light that reaches you is just not enough to trigger your eyes. So it's just a matter of that our eyes aren't sensitive enough. So the whole point of the telescopes is to make up for that by being much more sensitive than our eyes.
I'd just like to add that my favorite scientific instrument is telescope. There are many telescopes in the department, and I love to set up telescopes and show students what the universe looks like when you look through a telescope. It's really amazing. So if you haven't done that, try it. Yeah.
I'm not sure whether that was the intent of the question as well, but there is another reason why some stars are not visible, and that is because they are so far away, for example, 15 billion light years away, that the first light that they have ever emitted from the beginning of time still hasn't reached us. So it's beyond the so-called visible universe, too far away, right? We'll see it in another billion or 2 billion years' time, okay? Any other questions, hands here? Yeah, here. Yeah, I have, I'm faced the problem of light pollution here. So.
Good evening, professors. I have two questions. One of them is, like, when you focus and looking at the sky, like, you originally won't see it, but then you'll eventually see more and more stars. What causes that to happen?
Yeah, that's also quite simple. Your pupils would dilate when you go into a dark place. So normally, if you go into a room full of light, your pupil is very, very small. That's to protect your eyes, of course. But when you go out to a dark place, dark sky and so on, then your pupil will dilate, and then you see more and more light. Okay? So you need to adapt to the light environment.
Yeah. And, like, referring to his talk about the neutrons, can things inside the black hole still be able to feel or receive neutrons?
We cannot know anything inside a black hole from outside. So.
Okay, thank you all. I am afraid we have run out of time. I see 000 in front of me. So thank you all. In particular, I want to thank Simon from afar. Thank you for joining us here. And also, of course, to thank my friend MC for being on stage as well. In particular, to thank the audience, both physically in this room and online. I hope you have learned something, not just about astrophysics and astronomy, but about the endeavor of science. And at least you can take away from this evening a spirit of what science is about. And I hope that will stay with you as you move forward in life. Thank you and good evening.
Fantastic.
Thank you all very much.
Thank you very much, professors, for the great discussion and also answering our viewers' questions.